Hello, folks. Let's go ahead and get started. Let me grab some water right off the bat. I'm trying something new today. I'm actually streaming to YouTube, LinkedIn, and Twitter at the same time. It's the first time I'm trying to do this through Restream. So let's see how it goes. Software's a little bit buggy, but it seems like we got YouTube working, which is all that matters. Looks like we have a couple of folks as well. Some of the regulars, Julio and Lars. And then we have someone new as well. I'm quite excited for this session. It's going to be a little bit different than our previous sessions of actually any of our book clubs, because this time I won't be using a PowerPoint. I'll be using, or I should say, Google Slides. I'll be going through some notebooks instead. Our goal was to learn the basics of state-space models and notation so we can get ready for hidden Markov models. There was a lot going on in this particular reading. We were reading across a lot of different chapters and readmes and code, so it was a little messier, let's say, or fragmented from our usual read a certain chapter or read a certain topic. So let me know what you folks read. I saw in our community, folks were already showing off some stuff. Let me pull that up. Oh, wow. Oh, I gotta fix that. 1 second. There we go. Oh. Let me get this going. One moment, folks. There we go. Okay. All right. Here we go. So in here, we had a lot of stuff going on with a lot of different readings across 8 different, all over the place today. 4 different sort of chapters and areas of the book, and then also other folks like Luke had mentioned. There's other places to read as well. So, if there's anyone in particular you were looking to talk about, let me know. Otherwise, I'm going to go through the basics of Bayesian inference, notation, and then also state-space model basics in 3 parts in this particular club. So, with that, I'm going to go ahead and get started. I haven't seen any questions on the chat, so let's get to it. Let's pull up these slides, make them full screen. All right. So, as I mentioned, here's our agenda for today. Bayesian basics, which is this notebook, notation, and then state-space model basics. A couple folks had mentioned that they were coming from a frequentist background, so they would have appreciated this overview of Bayes' theorem. So let's go ahead and do that. This is the formula right here. Looks complicated. There's a lot going on. Symbols all over the place. We'll talk about notation in the next section, but there's just a ton happening. What I would say, especially for this club, and if you're new to Bayesian basics, it's really just the intuition that matters. The intuition is much simpler than the formula. Basically, you have some prior belief. It might be opinionated. It might not be opinionated. You get some data, and then you update your beliefs. That's literally all there is to it. That's the entirety of the Bayesian update. It doesn't have any of this sampling frequency stuff or sample size stuff or any of that. You don't really need it for Bayesian intuition. You just believe something, you get some data, and you update your beliefs. So a good example is if you're watching this live stream for the first time, you maybe had some idea of how it's going to go. Maybe you thought I'd be average. Now you have about, let's say, a minute's worth of data, and you update your beliefs of whether this is the right stream for you, whether I'm a good presenter, things like that. It's the same learning process that we all intuitively follow. That is the Bayesian update. And that also is going to be a large part of what state-space models are going to be, because especially in this book, they're written with a Bayesian framework in mind. So that means as we see data, we'll update our state, we'll update our beliefs of the hidden parts of the world, and then even the things that we'll see next. So when we get later to notation, there's a lot of symbols in this particular textbook. Math, the calculus and probability definitions can have a lot of symbols. So what I like to do is really break things down into their basic concepts and then learn what symbols represent what. So instead of referring to this, which is mathematically correct but has integrals and differentiators and given signs and thetas, and you don't know what's a random variable and what's a vector or a scalar, we're just going to focus on the basics. So like I said before, the prior is your beliefs prior to seeing data. Likelihood, how believable the data is given your model parameters. Posterior, that's your beliefs after combining what you believed before seeing data, the plausibility or the believability of the data, and then marginal likelihood. Right now, these words will probably not mean too much to you, but at least you know there's 4 basic concepts. So let's go through a typical Bayes 101 problem. And I pulled these straight out of Kevin Murphy's book. It's going to be, I don't know if he has coin flips, but he definitely has COVID and the Monty Hall problem. We're just going to cover the first 2. So the example is in section 2.3.1. And you can go through and read the example in the book directly. I've taken the example and I put my own numbers to it. But the idea is some percentage of the world has COVID. We make an assumption that, let's say, 10% of people have COVID, or in this case, I'm calling it space flu, which is why it's SF. So 10% of people have space flu. 90% of people don't have space flu, conversely. The challenge is you don't know which people have space flu and which people do. That's the real trick of it, right? Just like any disease, especially COVID, the trick was you didn't know who had COVID and who didn't have COVID. Now, to update our beliefs about COVID, a good thing to do is take a test. Every test in the world, though, has false positives and false negatives. So the chance of getting a positive test while you have space flu is indicated up here. And the chance of getting the chance of getting a positive test while you don't have space flu, so don't is indicated by the tilde, is this mathematical symbol. And here's what these probabilities are. The probability of a positive test when you have space flu is 90%. That's what we would want out of a test, right? When you have space flu, you'd want the test to largely detect that. And then when you don't have space flu, it's still going to say that you have space flu with 20%. So even if you take a test and you don't have space flu, there's a 20% chance that it'll show positive. A lot of numbers here. So let's just do the Bayesian calculation in code. We have our prior and we have our likelihood. Remember, our prior is before seeing any data, what we believe to be the fact about, let's say, a particular person or group of people. The likelihood is the believability of the data given given a parameter. So in this case, the data is the test, and then we know whether, the hidden state is whether we have space flu or not, and the data is whether we got a positive test. We run the numbers, and what the entirety of this calculation means is that even after a positive test, there is only a 33% chance that you have space flu. I'm going very quickly through this Bayesian update. So if anybody has any questions, you should ask now. What I'm going to get to is the visual explanation of this. And once we get to the visual explanation, I'm going to cover it all back again in detail. What's happening here in the math is we're just doing the Bayesian calculation. We're multiplying the likelihood times the prior, and then we're also calculating the marginal likelihood, and then we do the division, and we end up with these numbers here. Yep. Let's move ahead. So this is a lot easier to understand with a visual. So I'm going to show you this video that we pulled out of our practical MCMC course. So what we have is we have 100 people, 10 by 10 dots, and we don't know who has COVID and who doesn't have COVID. Now, for the sake of the example, we're going to highlight the people that have COVID, which are here in red, and then we're going to highlight the people that don't have COVID here in green. In the real world, you wouldn't know this by visual sight, but we're going to start with this so we can see the rest of the updates. So in the real world, everybody would still be a gray dot, but for the sake of this example, to make things easier to explain, we're going to color the dots with the hidden state of people's either diseased or undiseased state. We apply the test. Now the test has a certain faultiness to it, right? That's that false positive rate or true positive rate. So what happens is that even if you have space flu, the test only 90% of the time will tell you that you have space flu or COVID. So in this case, 9 out of the 10 dots have the red border indicating the test result. And one of these people has COVID, but the test shows that they don't, which is green. Likewise, in the healthy group, you have so many people that don't show positive. That's the green on green. But then even of the people that are healthy, 20% of them will show as having COVID or space flu, and that's indicated by the red border on the outside. Now what we can do is we didn't know without the test who had COVID and who didn't. Or sorry, our prior was that 10% of the people had COVID. So what the Bayesian update is it takes this, it takes the dots and it separates them. And now from the people that tested positive, so we have data of them testing positive, we are now fairly certain that 33% of them have COVID. So even with a positive test, we're now more sure than we were before. We're up from 10% to 33%, but we still aren't completely sure who has COVID and who doesn't, but we're closer to the true answer. Now what we could do, which is something that has been, which is what people have advised. Oh, I should turn my capture card off, I'm sorry. Now to follow some real world advice, what you do is you take multiple tests. So now that these folks have tested positive, you take another test to see whether it turns positive or not, and that gives you a really, really high probability of knowing whether you have COVID or not. So I will leave this example up to you folks to do this Bayesian update again, but that's all the Bayesian update process is. It's you start with a prior, so 10% of people have COVID. You apply some sort of test or get some sort of data. That data could be the test, it could be the cough, it could be any sort of thing. And then that test with a certain probability will also then tell you whether you have that disease or not. And so if you get a positive test and you have a cough, you likely have COVID. But if you have a positive test and you don't have the symptoms, then unlikely you have COVID unless you take another test, and then it's very likely you have COVID. This is a good explanation in the pandemic of why we had a lot of these recurring tests. They'd want you to test at different intervals, for instance, for time-dependent effects, or they'd want you to have multiple symptoms. All that's happening is the Bayesian update, but in practice. What you can do to see the mathematics of it is go through this notebook or through Kevin Murphy's book, and you can correlate that calculations with this visual, and that hopefully gives you enough intuition for the Bayesian update process that you'll need for this particular book club. I am going to pause here for 15 seconds because that is an extremely, extremely fast overview of the Bayesian update, probably the fastest I've ever done. A number of you said you were already familiar with Bayes' theorem, so this may be review for you. But if you are not familiar with Bayes' theorem and you want me to explain anything more, go ahead and leave a comment or a chat message so I can get to it in the Q&A. What I'm going to do now is I'm going to talk about different ways to do the Bayesian update in another example while we wait for questions. So what I covered was, let's call the classical Bayesian update. There's this other thing in the next section, right after the one we just covered in in Kevin's book, ProbaMill, that talks about inverse problems. And these are actually much more interesting, way more interesting than the Bayesian update of the probability style. So as it says here, probability theory is concerned with predicting a distribution over outcomes Y given knowledge or assumptions about the state of the world. By contrast, inverse probability is concerned with inferring the state of the world from observations of outcomes. In my line of work, this second thing, inverse probability, is much more interesting than probability theory. So probability theory largely is you have all these probabilities that are predefined. They come from somewhere. When you're reading a textbook, you usually don't know where they come from. They're just given to you. Very rarely have I walked into a business setting and I knew the probability of everything written down on a neat table. Almost always I have to do inverse probability, which is where I see certain events happen in my work or my life, and I have to infer what the latent state of the world is. The rest of the book club, that's what we're going to be doing. We're not going to be doing probability theory. We're going to be doing this inverse probability calculations, where we see observations about the position of the moon lander or the dishonest casino, for instance, and we're trying to infer what the state of the world was given those observations. This is the key change you have to make in your brain from going from probability theory to what we're doing with here. So we're not using the probability theory version of Bayes' theorem, let's say, but we are going to use the inverse probability thinking of Bayes' theorem. So we see something, what do we learn? It's not we know something, some probability values. What is the probability of some sub-event occurring? So let's go through another example. This is a fairly classic one, one that I use quite often in the courses and is also in Kevin's book as well. It's the binomial examples that come right after this, the inverse probability thing I just showed you. But let's say we have a website, 100 users visit us, 8 convert. What do we believe the unobservable conversion rate will be? So the first question is, what are possible conversion rates? Well, out of these are all plausible conversion rates, right? They could be 0%. You could have no one convert, 31% of people convert, 99% of people convert. The fact is, anything between 0 and 1% is possible. So the conversion rate could be anything, and what we have is a sample of 100 people where 8 people converted. So in our sample, the conversion rate is 8%. But in the true reality of the world or the hidden state of the world, the conversion rate still could be anything. What we can do as people is we can say we have a prior. We don't know what the conversion rate will be at all. All of it, everything is equally likely. I have no idea. This is the first time I've ever deployed a website. This is called an uninformative prior. You could have informed priors where you have different beliefs you start with, but I'm going to start with what's called an uninformative prior because it's the least contentious. Now, we get some data, and what happens? We see 8 conversions. We see 100 people visit, which means we have 92 non-conversions. And then this now is our posterior plot of our plausibility of conversion rates. This is the Bayesian update. It looks really easy, and it is because with conjugate models, which is what this is, it's just a mathematical formula. You plug in some numbers in a particular way, and you get the posterior. The reason we can do this is because people have done clever mathematics on pen and paper that let us just get to this answer. And it makes it easy for the people like us who can just take the solved solutions and write this calculation in Python, just like this. I already covered that one. So while we can do this with pen and paper, like this, and just plug in the numbers, in the modern world, we also can use probabilistic programming languages. So what we've done is we've restated the previous The previous model, we have our beta prior, which is the probabilities of conversion rates. We have the binomial number of visits, and we can define a model this way. We sample and we get the same graph, a very similar thing where our posterior plot of conversion is down here. There's a thing over here that's a diagnostic, which is our trace plot. And this now is not made possible through, let's say, pen and paper math, but it's made possible through computers and other people who knew the math to enable this particular formulation. So we have two ways of solving this problem. We have the same model, same question, right? How many people are visiting our website here? What's the plausibility of our conversion rate? We can solve it one way, which let's say is the old-fashioned way with pen and paper. And we can also solve this by expressing it to a computer and letting the computer do repeated calculations to estimate the answer. The key question here is, what's the difference? The conjugate model is pen and paper math. No computer needed. It's exact. The challenge, though, is it's very restricted to things that can be solved on pen and paper. Now, we also have this algorithm called MCMC. It's not very practical without computers. I should finish this out. Enables general models. Enables more models to be solved, and it's generally applicable. So we have the same model. Let's say it's a state space model. There were ways to solve it in the 1960s or the 1950s when we were launching people to the moon and had very restricted computation. And now with newer software packages, there's new ways to express it and there's new ways to solve it. The reason I bring this point up is that one very interesting thing about this book club, and in particular Dynamax, if I pull it up, is I'm really interested. I'm very interested in what was possible with state space models with, let's say, conjugate pen and paper solutions that we're going to read in the book through mathematical formulas and doing things by hand. But I'm also very interested to see what is possible now using Optax and Hamiltonian Monte Carlo, which is an MCMC variant, and sequential Monte Carlo. Because now we have computers, there's more we can do with state space models or Bayesian models or many other types of models than we could do with classical solutions. And in my own particular life, I found that what you tend to find the most material of is these classical solutions repeated over and over again in many different textbooks. So because they've been around for 30, 40, 50 years, they tend to just be in a lot of different textbooks, including this one. So you see them over and over again. And then another thing is, I don't want to call it a bias, but because they're precise and exact, you see them referred to more in traditional academic literature, much more than newer computational solutions that they're not maybe proven yet from a paper, but they work. And also they're just newer, so they don't have as many papers or books published on them. But they tend to be the ones that are the most useful for a lot of work that I tend to do. That's why I bring this up, is in this book club, I'm going to be very, very interested in seeing what the state of the art is and not just covering classical solutions over and over again. I am curious what folks think about that, whether folks wanted to see the classic way of doing things or folks wanted to see the newer way of doing things. Of course, we're going to try and cover both, but I'm really fascinated to see if folks want to go one way or the other. All right. Double checking that my microphone is on, because I assume if people couldn't hear me, they would have told me by now, but I'll also make the assumption that you guys are so enamored by this lecture that there haven't been any questions yet. All right, a couple typos. Sorry about that. So, in relation to this book club, as I mentioned, there are various pen and paper solutions that state space models, but tools like Dynamax have different and more complex solvers available, so we're going to want to go through that. I just showed that Dynamax supports MCMC methods as well as Optax and sequential Monte Carlo, so we might see that later as well. Really, really fascinated to see how these newer methods let us expand what we can do with state space models. So like I said, we want to learn both the traditional techniques and what newer tools like Dynamax let us do. So for the last example in the Bayesian update, what I want to show you is a linear regression example with MCMC solutions. The reason I'm doing this is I just want to give you an example to show you, especially for the folks who aren't so familiar with Bayes' theorem, that it's not just this probability calculation that you see, and it's not just coin flips and COVID, but rather you can expand this to a general class of models. Of course, you folks being here in the State Space Book Club, I would expect that you are well aware that we're going to be using these methods for state space models, but I want to reinforce that these ideas between Bayes' theorem, just the core idea of seeing data and updating your beliefs, is not just restricted to coin flips and COVID and really basic things like that. So here's an example of the Palmer Penguin data set. Let me just pull this up because it's just such a cool data set. So I'll show you a picture. It's part of the reason we do a live stream. So Palmer Penguins is one of the new cool data sets you'll see over and over again because it has just a lot of interesting attributes that make it a great data set for machine learning or neural nets or any sort of data problem. First off, it's got a bunch of continuous attributes like bill length and fin length. Let's see if I can find you the picture right here. Bill length, bill depth, Kalman depth. It's got the year that the data was collected. It's got this the weight of the penguin, and it's also got the species. So you got some nice categorization going on here. So it's really got everything. It's a nice, small, tidy data set. And what we want to do is we want to run a linear regression, very similar to this one. We'll do it for all penguins at once, but we want to understand if as one portion of the penguin varies, whether its weight goes up. Very classical problem. So let's jump back to our picture. So here we go. We have flipper length and we have mass. And the question is, as penguins have larger flippers, does their body mass in grams go up? Logically, as a person, I would say yes. I would think that as the penguin gets bigger and has bigger flippers, it weighs more. We have some data here, and without just the math and just some intuition, I can kind of tell that this line goes up, that my intuition has been matched. But what we want to do is we want to use our awesome Bayesian skills to figure that out. So we plug that into a probabilistic programming language such as PyMC. In here we have the linear regression right here, an intercept, a coefficient, flipper length. We have mass, and we're trying to estimate that. And we run our Markov chain Monte Carlo sampler. I always mess that up. Sometimes it's Monte Carlo. No, it's Markov chain Monte Carlo. MCMC confuses me because it's two symmetric words. Anyhow, point being is we can run our sampler and we get our regression right here at the bottom. So now we can see that we have our mean regression line. This is what every regression package will get you. But the nice thing, because we're Bayesian, is we also get these uncertainty bounds to tell us that this could be the one regression we get, but we could also have one that goes this way, maybe a little bit steeper. We could have one that goes a little bit shallower. We have both plotted here, and we're using all of our RVs and PyMC code to make it happen. The takeaway from this is that you can use Bayes' theorem to update your intuition about anything, any class of model, any type of model. So in this case, here's linear regression. People don't usually think of it as a probabilistic model, but it is probability, right? There is a probability that this is the mean, and we can use Bayes' theorem to help us plot what that probability is with covariates. This is going to come up often on our book club. We're going to start with models that don't have covariates, but we're still doing Bayesian updates. Those are going to be hidden Markov models that we're covering next. But as we get further into the club, we're going to have state space models that have covariates, right? They're going to be extra pieces of information that aren't hidden that we can observe. Like, I'm trying to make one off the top of my head. But we can observe things like if somebody's sick, right? With COVID, we can observe whether they have a cough or not. We can observe their temperature. These are covariates that can then be plugged into a model that helps give us information about the latent state of the world, which is whether somebody has COVID or not. It's a prime example right there. We also have the duration that somebody tested positive, right? So I won't bring this up here, but we developed models in PyMC and with Bayesian updates that told us that from time of test, what's the probability that somebody will be positive on day 15, day 16, day 17. These are all state space problems, right? We can model that as a state space problem. Time step 0, 1, somebody tests positive. Time step 15, they're still testing positive, but do they have COVID? I don't know. Getting ahead of myself there with the time steps, but honestly, super fascinating stuff. It's absolutely why I love statistics. I'm getting all over the place. I'll refocus here. So here's the takeaway for Bayes' theorem. It's just a philosophy for how we can update our beliefs given observations. This is a common theme you're going to see over and over again. Probabilistic ML, the book, Kevin calls it outcome belief mapping, which is inverse probability. That's what we're doing here. We're really interested in this outcome belief mapping. We see a bunch of outcomes. We want to understand what our beliefs of the world may be or map them to our beliefs, which is inverse probability. What we care about is this thing called relative plausibility. I didn't mention it so much in the previous slides, but we don't care so much about the exact probability somebody has COVID. We just care relative to our prior beliefs, whether we believe more likely that they have COVID or not, let's say. And it'll be the same for a lot of the problems that we work on. The last thing which we covered is that for the same model, there can be different estimators. So we had the COVID example, and we had two estimators. We had conjugate estimators. Well, in that case, the conjugate model, it's not an estimator, it's a exact solution. But the point being is we had one way of solving and calculating our distribution, our posterior distribution. That was with the conjugate update, to pen and paper math, as I called it. But we also had MCMC, which is an estimator because it's not exactly precise, but it's a practical tool that computers afford us to estimate the posterior probability of these models. That's a fancy way of saying there's two ways of doing things. Each of them has their trade-offs, and computers enable us to do things that weren't possible in the past. So a theme you'll see in the State Space Model Book Club is we'll see the traditional solutions. They will be there because they've been there for a long time. But I am very, very interested in what the newer solutions like MCMC enable for us. Do they let us express more complicated models? Do they let us solve types of models that we couldn't have done in the past? What does Dynamax do that couldn't have been done with pen and paper? With that, that's the end of the Bayesian intuition and the framing of this particular book club. We're going to have two more notebooks like this one. The next one will be notation, because a couple folks asked how I learned notation. A couple folks asked how I learned notation. And then the last one will be state space model basics. But I'm going to pause here and I'm going to check the questions. I believe one came in. Rahul asks, how do you specify priors? I see that the standard deviation you specified is half student t. Why did you select that particular distribution? All right, super common question in Bayes' theorem or life in general. So the question is, there's two questions here, and I'll break them apart subtly. One question is, why do you specify the model the way you specified the model? The second question is, how did you pick the parameters of the model? So for the first question, why is the model the way the model is? The unsatisfying answer I'll give you is that it's the classic George Box thing that you've probably heard 1,000 times, is that all models are wrong, some models are useful. So like the name implies, this is just a model of the world. It's, in this case, how I chose to represent what the relationship between flipper length and the weight of penguins. There's no written rule or fundamental truth that this has to be the only model of the world, and this is the only way penguin length and flipper length relate. I could have related them with square root or anything else like that. And to that subtler point, there's no precise way of saying that this is the only way that the variability of mass could occur from the mean. That it had to be half student T distributed, that it couldn't be half Cauchy distributed, that it couldn't be flat, a uniform distribution. It could be anything. But looking at the data, as a person who's done this a lot, like it looks approximately like something that would be a half. Looks like something that would be half student T. Could be half Cauchy as well, because it starts high and then it looks like it'll drop off, and it's not a huge number. That's my one way of answering your question, Rahul. That as a modeler, I picked it and this was my choice, and I think it's reasonable, and I'll stand up and I'll defend it. Another reason I picked it, from a computational reason, is that I don't believe the standard deviation of this thing is massive, right? I don't think it's going to be some huge number. So computationally, I want my sampler to stay in a space of where I believe there's plausible values. So I picked this particular distribution and these particular parameters because they were within the reasonable range of parameters that I wanted the computer to stay in. This way, the sampling could occur faster. So one way was I'm a statistician, and I am expressing that this is my belief of the way the world works, or at least close enough that it'll be useful for the question I'm trying to answer. The second way is I'm a computational statistician, and I'm picking parameters that help my model converge to what I think is going to be a reasonable answer. The reason both are important is we're going to see both in the State Space Model Book Club. I think it was actually even mentioned already. The second one was already mentioned in our book club. Let me try and find it. This thread here, there are folks already talking about convex solutions and non-concave things and which solutions things come to. So there is a model of the world, and this model, if specified correctly, can help you find an answer that's useful. But because it has certain properties, it makes it harder to find that answer. So that's one part of the thread. The second part of the thread, and we'll see later, is that sometimes you, as a person, you want to push the computation to go one way or another because it'll give you more reasonable answers that you know as a human. This usually becomes the point where folks get uncomfortable, especially folks that come from frequentist backgrounds, and say that that now you're introducing bias into the problem, or that this isn't. If somebody picked different parameters, that things can be different. That is absolutely true. I won't dispute that whatsoever. Unfortunately, the answer I have, sometimes the situations you're in, you have the data that you have, and you still need to come up with a data-informed answer. So for me, in my work, it's been better to write down my assumptions and note them down cleanly, and then explain what my answer is backed by data rather than wildly conjecture what the particular solution will be. So again, Rahul, I think I gave you 4 or 5 answers about why we specify priors the way they are. The neat wrap-up of that, if I go forwards to backwards, is I have a problem where I want to get a reasonable answer. I need to make a model of some type to be able to come to that answer in a way that isn't just me wildly guessing. What I'm doing here is I pick priors that I feel like won't influence the answer too much, but are within a reasonable range. And I'll pick those priors based off of either my prior experience or based off of me knowing I need to get to a solution with a computer and I don't have infinite time to wait. So those are the 2 reasons to pick priors. And then for the inevitable question, does that bias the solution? In some sense, yes, because I'm picking stuff. Is that better than wildly guessing an answer based off of just looking at a chart? I think so, yes. And in a perfect world, would I always have carefully constructed experiments that eliminate all bias? In a perfect world, yes, but in a lot of times we don't live in a perfect world, which is another reason I'm excited for the State Space Model Book Club, right? The dishonest casino is an example of a statistical problem where you don't have a perfect experiment, right? You don't have these randomized control trials. You can't just run 1,000 casinos and see what happens. In real life, you have dishonest casino examples happening all the time. I will get to that example once we get into the third part of this book club. But these things are running all the time, and you still need to make inferences. What are you going to do in those situations? You have to use things like space models and make some assumptions to start moving things in the right direction in practical scenarios. So this was great. This was actually, like, we covered everything in Bayesian theory, and I was surprised. I was wondering if somebody was going to ask me about priors, because that always comes up. So I'm glad you did, Rahul. If you have any more questions about the basics of Bayes' theorem, probabilistic programming languages, priors, updates, types of things that can be used in Bayesian updates, do ask them in the chat, or leave a comment for folks that are watching later. I want to point out this was an extremely fast overview, like incredibly fast overview. If you want more of a background, again, Kevin does an amazing job in his book. It is chapter 2 here. So go to chapter 2. As implied, it's a pretty fundamental concept, which is why it is chapter 2. He covers basic probability theory here. Bayes' theorem is derived from that, and he shows it the derivations here. And then he covers a number of examples. So I think Kevin does a fantastic job showing a lot of these things in chapters 2, and then even chapter 3, where he does a nice comparison of Bayesian statistics, frequential statistics, empirical Bayes, so on and so forth. To answer your question, I'm not even showing my screen. I'm sorry, folks. Let me show you that again. Chapter 2, probability. That's where I'm pulling this up from right now. So he does a great overview here. It's a little hard to read on your screen, but let me make it a little bigger. I cannot make the contents bigger. Chapter 2, chapter 3, and then Rahul, your question has to do a little bit more with section 3.74, or sorry, section 3.8. Actually, the quote is right here. Didn't even do that. So section 3.8 will have questions about model selection, which is related to your question about how do you pick priors, and then the second question of, like, how do you know that you made a good choice of priors. There's a bunch of analytical strategies you can make. There's a bunch of qualitative strategies you can make. The analytical ones are discussed here in great detail, and then he also provides some qualitative overview as well. It's part of the reason I really love using this book. Kevin covers literally everything. Like, almost every question we're gonna have, it's gonna be covered in one of the 2 volumes, either the basic topics or the advanced topics. I also should point out, this is, I believe, the basis. I forget. He's got 2 books. I forgot which one this is, but hopefully you can figure it out. I will post that in the discourse community later. Okay, I'm gonna take a break, reset. Now we're gonna get into notation. So for folks that are new to these live streams, the live stream is approximately 10 to 15 seconds delayed from when I say something to when you folks see it. So feel free to preload your questions into the chat immediately. That way, when I reach a stopping point, I can get to them. Whew. All right. Moving on to the next topic, how I learn notation. So I want to point out, this is the way that I learn notation. It doesn't have to be the way that you learn notation, but I think something that you've noticed is there is a lot of notation in this particular textbook, an incredible amount of notation. And while I'd say on one hand, I wish that there was a longer explanation in the notation in the book, I'll also point out the book is already massive, and if every time we saw an equation and all the notation was written out, the book would be 10 volumes. So I think Kevin struck the right balance, but if you are not, certainly if you're not looking at these equations day in and day out, like even I'm not looking at these equations day in, day out, to be quite frank with you, it can be quite overwhelming. Nonetheless, we are going to learn the notation in this book, both because it's a learning club, but also because a lot of interesting insights are captured in the notation, and we don't want to miss out on that. So let's just talk about why notation. I saw that a lot of folks here I want to show these to you real quick before we move on. I wasn't sure what the background of folks here would be, whether they would be high school students or undergraduate students. From the folks that responded, it looks like a number of us have masters and PhDs, so and in technical disciplines. So I assume at this point we're not too scared of notation. We're not worried about it, but nonetheless, there is a lot of notation in this book and specialized notation. So why notation? It's the most precise way to represent math. I think we've all know this given our education levels. Also, there's no way to avoid it with the text we fix. So we kind of are or in it. We're in it. So we're doing it. It's really the answer for this book club. If we pull up the full state space model equation, it is a mouthful. There's a lot of symbols going on, from capital T's to lowercase t's. We got the uppercase pi right here. We got a bunch of p's. We don't exactly know what the p's mean, but in different cases they mean subtly different things. You got z's and u's and all sorts of stuff going on. So this is the full state space model equation. We're gonna get to this, not today though. We're gonna get to this eventually in probably 4 or 5 book clubs. But this is the full shebang. It's the entire space-based model equation in one shot. If we compare this to Bayes' theorem, this was the original thing we saw about Bayes' theorem, right? It was all these symbols. There was y's, there was priors and posteriors, and a bunch of capital thetas and derivatives, and there was a lot going on. But if you remember, you don't need to know all the symbols here right off the bat. You just have to sort of understand what's going on with this. The posterior, the prior, the marginal likelihood. Like, you don't have to memorize or swallow this all in one take, but really we could start with the simplification and then work our way up. So I don't know why my table of contents broke. I will fix this CSS issue. I don't know what's going on. But the way I like to do things is I like to start with the fundamental philosophy. That's what we did with Bayes' theorem. Just forget the math and the notation. Just what is the idea behind this? What's the idea behind a Bayesian update? What's the idea behind a state space model? I then like to find the simplest applied example. So I look for really an example that strips away almost everything and are numbers that I can, like, sort of, let's say, hold in my hand. Like, I can say this is the probability of space flu, this is the probability of COVID, and get a feel for what everything is with very, very basic, ideally scalars, but just really, really basic stuff. These days, I typically do it in code. This is something that's evolved over time as I've continued to learn past college and self-learning statistics. I'll try and find code because code has no ambiguity. You can look at code and you know exactly what things are. The problem with the notation on a piece of paper is you can't see past what that thing is. But with code, you can expect it. You can see whether it's a NumPy array or a random variable or whatever it may be. So I typically try and find a simple example in code, just like I did with the COVID example. And then I'll implement it myself. So an important step is I have a tough time retaining things if I read them, but I do a better job once I've gone through it once myself. So with the COVID example and when I was learning Bayes' theorem, I would just write out the computations that you saw in the last chapter on my own, and I would see how it works. And then really it's just a matter of adding complexity one step at a time. So then it's a matter of saying, okay, what's the next thing I can do to make this a little bit more complex? So rather than using the probabilistic version of Bayes, maybe I'm going to now use the inverse probability method of Bayes. With our state space model book club, we're going to start with hidden Markov models. You'll see why in a second. And then we'll move our way up to more complex models that have more states, maybe moving from categorical predictors and states to continuous emissions, things like that. So like I said, this is exactly what we just did for Bayes' theorem, and we're just going to do this over and over in this particular book club to break down the state space model equation. So like I said, this is Bayes' theorem simplified, way less intimidating than the full expression of Bayes' theorem with the integrals and everything like that. We just took this, we worked our way up to linear regression, Man, I really got to figure out what's going on with these my CSS here, but I'm just gonna do this in Markdown format because things are broken. So what is the math I'm dealing with? Probability distributions, integrals, whatever it may be. I want to figure out what's going on, whether it's a scalar, a vector, a matrix. Figure out what's a real number, indicator, random variable. It's just what is the thing, and then paying attention to shapes. So this is a little bit one step down. This is how I kind of approach a problem. So to talk you through one, because I have a dual background now in mechanical engineering and statistics. When I'm doing mechanical engineering, I'm like, okay, I'm probably not dealing with probability and distributions or integrals. I'm nearly always dealing with scalars. Like in mechanical engineering as a field, while everything could be represented as a distribution, the fact is mechanical engineers typically don't represent things with distributions. I'll just do this in this view. So I know when I'm looking at a mechanical engineering text that it's basically not going to be a probability distribution. Like I just know that because that's mechanical engineering people don't do that. When I look at Kevin Murphy's book or an Andrew Gelman book or my book now, there's going to be a lot more probability going on, distributions going on, because that's the topic at hand. It's statistics. And with that comes different assumptions of notation, different assumptions of what you can do with the mathematics of it. Which leads me to my next step is figuring out, again, what is the thing? Is it a scalar? Is it a vector? Is it a matrix? That changes the computation and the meaning a lot. There's a whole bunch of other like subclasses of this, whether it's an integer, a real number, Boolean, indicator, whatever. And then I'm just going to keep saying shapes because shape problems are like a thing that happens in computation all the time. And so knowing the shape of things is essentially knowing point two. Geary says, when you cut it up, do you use a notebook? Do you find a debugger makes things to understand it easier to understand correlation between notations and variable and code? When I code things up, I typically I use both a notebook and I use also an IDE. The reason I say I use both is a notebook makes it easier to see visual outputs and interactively code. So if I'm just coding quickly and I want to see the outputs and learn fast, a notebook is nice. So I can quickly iterate, see outputs, see what objects are. The trick though is when I use libraries like Dynamax, I often then switch to using like Visual Studio Code or PyCharm, because the computation is often hidden one layer beneath the surface. So just looking at the output from those libraries gives you the output, but it doesn't tell you what's happening underneath. So when I was learning how probabilistic programming languages work, like PyMC for instance, when I was dealing more with model outputs, I would use notebooks. But when I was dealing more with like what is happening in the probabilistic programming language, I would use PyCharm, because PyCharm would let me dive one layer deeper. I'm going to just quickly jump out of this again. One piece of feedback I would like from you folks, actually right off the bat with this book club, is let me know whether you'd like me to stick to the script, which is the notebooks, or whether you like me going off these tangents. This is me updating my Bayesian prior, so whether you like the off-the-rail stuff, or whether you like the on-the-track stuff, would really appreciate that in the discussion. While you tell me that answer, I'm going to go off the rails and I'll just show you Dynamax. So with Dynamax, a lot of the computation is going to be happening under the hood. You declare a model, like a hidden Markov model, with a high-level algorithm, but then beneath the hood, there's going to be these categorical HMMs or GLMs or whatever we're going to be doing. So I'll probably be using both notebooks, and I'll be using PyCharm. I'll be doing both because notebooks will help me. Well, the notebooks are literally what the documentation is written in. So we're going to be using notebooks because the docs are notebooks. So that's one easy answer. We're going to be looking through Casino HMMs, and because this is a notebook, I will be going through this as a notebook. But I also, let's say we call HMM smoother, I want to know what's happening in the smoother, so I'm going to probably copy and paste a lot of this code. Classic example where I don't show you what I'm looking at. So this is the notebook, and I'll be showing you this notebook. or we will be going through the notebook. But let's say once we get to this thing, the hidden Markov model smoother, we want to know what's going on under the hood. So then we'll jump to the code and we'll find this. We'll find the smoother in here. I don't know where it is, but somewhere in this code base is smoother. And then we can look deeper to see what's happening in that particular method. So short answer, I use notebooks and I use PyCharm. Notebooks when I'm looking at outputs, such as this one, I want pictures and graphs and want to go quickly. But then a debugger when I want to see what's being called. So an example here is I want the notebook to see the smoothing output, but when I want to see what's going on in the smoother, I'll use a PyCharm or a debugger to then dive into wherever this smoother is, because I don't know where it is right now. All right, and one last pitch to tell me, you guys, whether you like the off the rails format or whether you like the stay on the track format. Happy to do either. Jumping back on the rails, rather than start with the crazy version of state space models, which is the one we saw prior, we're going to start with this very simplified version. So this is the simplest state space model. This is the hidden Markov model for this is the hidden Markov model for categorical distributions or discrete outcomes. So both discrete states and discrete spaces. I will explain what state and spaces are in a moment here. But this is the simplest version of the Bayesian of state space models, and it's the one we're going to start with. So to show you the difference, I'm actually just going to copy and paste the difference live here so we can see it for ourselves. Let's take this, do some live coding here. Why would I have a notebook up if we're not going to do a little bit of live coding? All right, so you can already see there's a lot of differences between the two, right? This is the full state space representation that we're going to eventually get to once we get to the most complicated models towards the end of the book club. But at the beginning, we're going to start with by dropping this U, some of these covariates. We're going to pick up this theta, which I'll talk about in a second. We're going to drop a lot of these other terms in here as well and simplify them down to a couple terms with A and B, these two matrices, which again we'll talk about in a second. And rather than using the generic form, which allows for continuous and discrete distributions, we're just going to stick with discrete categorical random variables here. So no generalized distribution, but categorical variables. Love categorical variables or categorical distributions because there's a discrete amount of outcomes, really easy to visualize in your head. You can pen and paper it quite easily by just by looking at a bunch of coin flips, as we will be doing in this upcoming week. So we're starting here. We're going to work our way up to up here. Getting back to the point of notation, again, I will fix my CSS, but what I suggest for you, develop a strategy that works for you, and that's literally my first thing. So it takes time for you to learn what the best way for you to learn. That's part of learning. And you should figure out a strategy that works for you. You can try and use mine, but I suggest you find the combination that works for you, whether it's my thing or your thing, whatever. Maybe it's reading, maybe it's note cards, whatever it may be. Use code examples and note cards, whatever, again, works for you. I actually really appreciate this community because we can leverage each other as well. If we're confused about a term, we can ask each other. So other people are a fantastic resource. We're going to learn this all together, but actually it'd be a pretty good thread to share how we all learn notation. So I'm going to start that one right after this. The biggest thing though is really don't get frustrated. You can do it. It's just like learning a language. Everybody is capable of learning a language of some sort, whatever that language may be for them. And this is the same thing. We're learning a language. There's maybe specific terms that are used that are for this particular book, but that doesn't mean that you can't understand the concept, right? I understand the concept of water. I understand the concept of running. If somebody told me that I needed to express those concepts in a language like Tagalog or Chinese, I would have no idea how to do that. But that doesn't mean I don't understand running or water. It just means I don't understand that language. So it's the same thing here. If you don't understand the notation, that doesn't mean you can't understand state space models. It just means we have to get acclimated to the language and the ideas, but you will learn state space models out of this book club. So for our recap for our second part, notation can be challenging, but we should learn it, especially so we can communicate with each other. I would advise breaking it down one step at a time. A good way to do this is learning the meaning, not just what the symbols mean, so not just what theta or p is, but really what's the meaning behind these. And building things in code really helps me. That's my particular thing. It's actually one reason I really like being a computational statistician, is that I work best when I'm working with code. I struggle a lot when I'm working with pen and paper, so I tend to stick with code. It's another reason I picked Dynamax as this book club. Heavy bit of bias there. That about does it for our notation section. So we got 2 out of the 3 down. Thank you for sticking with me. Again, let's ask any questions. Let's see if anybody said anything. Wojasny says, kind of hard not to go off the rails. It's pretty natural. Thank you for confirming that it's pretty okay. There's just so many things out there and so many different resources that I can't even think of them even before the book club. As I'm talking, they come to mind. So thanks for the confirmation there. And Girish says that makes sense. So it looks like we have everybody. We are good to go. All right, we got 2 things on the fundamentals, and we're going to be on our last topic, which is the state space model basics. So now we're going to dive into the topic that you all came here for. It's the one that is in the title of everything, which is state space models. Make sure I show my screen. We're going to talk about the basics of state space models to work our way up to our next week's reading. So there's 2 parts of state space models. I'm going to pause here and let you folks take a guess at what those 2 parts are. I have a high prior that you're going to get them. I'll wait here for about a second or 2 before telling you that they are the state and they're the space. I know. You came here for that. This entire book club. It's a wrap. No, I'm just kidding. Obviously, the one thing I like about state space models is that unlike some crazy name like neural network, which doesn't really tell you anything about what the model is, or generalized linear mixed models, or media mixed models, where you're like, you hear this name and you're like, I have no idea what the hell is in this model. Like, what is it doing? What's going on? Things like stochastic gradient. Well, I guess that's an estimator. So, what's another one? Support vector machines. That's another one that really got me for a while. State space models, it's literally right in the name. It's a state and a space. Like, I really wish more statisticians named their models after things that make sense like this. Like, I mean, I don't really know what a neural network is, just from the name. The good news is we're going to be covering, again, this basic version of the state space model. In here, there's a couple parts. There's actually one more part, which is the prior for the initial state. So before we see any data, what do we think is going to be there? Where do we think we are in the world? So in the dishonest casino, this may be what is the probability of the particular dice that we will get into in a second. But then we have the 2 other parts. This is actually where I'm not so happy with the state space model naming. There is what's called, I think I named this. Okay, I'm going to have to go back and revise this slide because I don't want to name this poorly. But there is the thing called the dynamics model, and it's also, I believe, called the transition model. I'm pretty sure it's called the transition model, and I just mixed up the typo here. So this is where we get into confusing naming. There are 2 names for this particular portion, the dynamics model or the transmission model, or transition model as we move from one state to the other. And then there's also what's called the observation model or the emissions model. So we have the state of the world, which is which dice are we using, and then we have the observation of the world, which is what are the dice rolls that we are seeing. In this book club, even I should turn this off for a second. I'm gonna mix these terms up a couple times to get them right till I reinforce them. Till I reinforce in my head enough to they're right. But they have different names. We're just gonna have to learn the different names, whether that be transition model or dynamics model or observation model or emissions model. The reason things come up with different names, fortunately or unfortunately, is state space models are one of these models that's used all over the place, like everywhere. I didn't realize this when I was a mechanical engineer, but when I was learning about spring mass systems, they're called spring mass damper systems. That is a version of a state space model. So mechanical engineers have a version of it. I read that econometricians have a version of state space models. Of course, statisticians have their version. So as different disciplines tend to pick up models, they tend to come up with their own names for things. That's what's happening here. Two different groups of people came up with the same model, and either they renamed it or they just picked different names. And we're going to have to learn both because we're learning about the models independent of any particular application area. In here, there are a couple of terms. So as I mentioned, notation, there's going to be a lot of notation in this book. It's going to be good to learn the notation. So we have three things going on. We have our transition matrix of probabilities. We have an emission probability here in B. And then we have our initial probability given here with pi, lowercase pi. And then we have uppercase pi for the multiplications. Again, don't worry too much if this doesn't make sense. We are going to be breaking this down over the next couple of weeks. The other part of state space models, let me make this a tiny bit smaller so it fits on screen. Maybe a little smaller. Okay. The other way to think about space models is visually, and so I highly recommend in areas where you get confused or the terms aren't making sense is to draw things out. The book is full with a lot of visuals and graphs and things like that, which we're going to use quite often. And we're going to start with this one that I pulled straight out of Kevin's book, and I believe he pulled this out of another book as well. But you have, oh man, let's see if I can get this right off the bat. I always mess this up. You have the state up here, which is the state of of the hidden state that we can't see, represented in Z. There could be some state at t-1, the time step before. There could be some state at t, which is where we're currently at. There could be some state at t-2, 3, 4, 5, way back in future. And then there's going to be a set of states that are coming after this, right? t+1, t+2, t+3, t+4. So we have these discrete states. That's one portion of our model. And then we have the things that we're seeing, which is the space. We see a particular outcome from a dice or from our sensor or from whatever it may be. And we end up with these things that are observables here. This diagram can get more complex. I'm pretty sure if you read the text, you saw the more complex version. But we're going to start with this basic version here. So what we're starting with is the dishonest casino. In the dishonest casino, as you probably heard me allude to a couple of times, we have two dice. One of these dice is, let's call the honest dice. It has an equal probability of having every face show up. So 1, 2, 3, 4, 5, and 6 all have 1/6 probability of showing up. But then we have a loaded dice. It's been weighted in some way, and it rolls a particular number more. I forgot which one was used in the example, but let's say it rolls the 1 much more than it rolls any of the other numbers. The challenge is we don't know which dice is which. The casino dealer is switching them in and out. So maybe this dealer has been bought off by somebody to help them cheat at a game of craps. Who knows what it may be. But this dishonest casino is swapping these dice in and out, so it makes it harder to tell that they're being dishonest. And what we have is we have the dice as represented by the hidden state. We don't know which one is being used at a particular point in time. We might have a guess, but we don't know for sure. But we do see the dice rolls. We see what's happening because that happens clearly on the board. You see the 1s, the 2s, and the 4s, and the 6s roll on the table. Now, this is the same setup that I just explained. One dice is fair, one is biased. The dealer swaps the dice at random. So this is a key assumption we're making, that the dealer is, whether it's some sort of random or whatever it may be, they are changing the dice out. Now, it does not mean that they're changing them. I want to make this clear in case folks are new with probability. It does not mean 50-50 probability that they're switching back and forth. Random just means that maybe 90% of the time they're using the fake dice and 1% of the time they're using the true dice. Sorry. 90% of the time they're using the dishonest dice, and 10% of the time they're using the honest dice. It could be 20-70. Random just means it's not fixed through some deterministic algorithm. It doesn't mean that it's 50-50 all the time. We may not know what the randomness is, but there is some randomness. Now with state space models, this is one reason I think that folks get confused learning them or maybe get overwhelmed at the start, is there are a lot of different ways to use this particular type of model. So often when you deal with statistical tests, it answers like one question, right? Like you get this like, I'm testing two websites out. I'm testing out website A and website B, and I just want to see if website B has a higher conversion. Or I just want to see whether somebody has COVID or not. A lot of models have like one set of calculations that answer one particular type of question, because it makes it really easy to learn, right? You really only have one thing that the model can do, so it fits really well in our heads. The cool thing with state space models, but also the confusing thing, is they can answer a ton of questions. So how can we tell which dice is in use based on the outcomes that we see? That's one thing we can do. We can do that while we're watching live. That's called online filtering. We can watch that after the fact. So maybe after a day of being at the casino, we're like, oh, I actually don't believe that casino is fair. We can now look at all of the things that happened and do what's called offline smoothing. That's one way to use state space models. This is an estimator trying to figure out what the state is. The next thing we can do is we can figure out what the next dice rolls will be. So maybe we're in the casino the next time and we want to know what's going to be happening. That's forecasting or prediction. This is like the moon lander trying to figure out where it is in space because it needs to actually like get to the moon. We also may be, instead of trying to predict the observations, we're trying to predict the next dice roll. So what is the next dice in play? Edit this out, fix that. So what is going to be the next dice in use? We can make estimations about the state of the world. And it's this complete bevy of options and state space models that makes them both so fascinating and so useful, because you can take one model and answer 4 or 5 different questions at the same time. But also confusing, because when you see different algorithms that we're going to see in a second, over the next week, some of these algorithms are used for online filtering. Some of these algorithms are used for offline smoothing. The mathematics is looks similar, but is subtly different. So it makes it confusing sometimes to separate the two. Just keep this in mind as we're going through the examples, because we need to be very clear about what question we're answering to then be very clear about what method is being used to answer that question and be totally confident about the whole shebang. So when I generalize these questions, if we see a bunch of outcomes, because that's all we can see is the outcomes, we can't see the state of the world, we can ask what will happen. We can estimate the state we're in, or what we'll be in. We can estimate what we'll see next, or we can estimate the underlying truth of the world. So we could estimate the transition matrix parameters. This are the probability of the this is how the dealer is switching the dice in and out. We can estimate model emissions, which is what's the probability of the dishonest dice showing a particular face value. We can estimate the starting point, which is where if we see an observation here, where did it come from? A particularly topical example that I'm going to use because we're having here is where did that Chinese balloon start from? That's a particularly good state space representation. We know where it ended up, but now it's a big question of where did it come from? And we know it came from China, but where in China did it come from? I'm going to pick on China a lot here because we have the COVID example, but like, where did COVID start as well? Hopefully nobody gets too annoyed at me with these two examples, but unidentified object tracking is a good example. There are examples we have from my work at SpaceX as well. Just like, where did the thing start? That's also an important question. So our state space model recap. This is our last recap for today. State and space, as the name implies, are the primary terms. There are other equally valid terms. Got doubling this up. Emissions, observations, transitions, dynamics. We're going to hear all these words over and over again. I'm going to make flashcards for them so I remember. In using state space models, we may be more interested in the hidden system state. We may be interested in what next immediately or what's to come over a series of time steps. We may care after the fact or during the sequencing process what states we were in, not what states we are going to end up with next. We may want to estimate model parameters. We may want to estimate what's next for observations. All of these are ways we can use state space models. All of these are things we're going to explore over the next book club. And we're going to start with the simplest case, which is discrete hidden Markov models. There are no autoregressive dependencies, which we're going to see later. There's no covariates, and as the name implies, it's discrete countable states, which makes them easy to work with. With that, you've made it through every single notebook. Start leaving your questions now. I'm going to go off the rails a little bit in a second, but let me know what questions you have, while in the next moments I'm going to explain what we're going to be reading next. So I'm going to put the full post on Discourse. It's not there at the moment, but we're going to be going through, as you probably guessed by now, the Casino Hidden Markov Model notebooks from Dynamax, from the Dynamax docs. So to show you where those are at, if we go here and we go to the Dynamax docs, it's going to be these two. We're going to start with these two because if we understand these two really, really well, we're going to have a really good, solid understanding of the rest of the State Space Model book club. I would rather us spend more time on this and get it right rather than rush all of HMMs and understand it poorly, because then it's going to get harder to go through the more challenging ones down here as we get to them. Another reading that was also mentioned, it's in Kevin's book, is reading through the entirety of this this particular blog post from the India Institute of Technology. So this was a light reading from our current week, but now we're going to do a full reading, and we really want to dig into all the bits and pieces here. They did a fantastic job breaking down the notation and showing us a bunch of pictures, and having even like live simulators to really help us understand what is happening here in this Markov chain representation, and then eventually state space models eventually hidden Markov models, which are state space models as well down here. So I want to say it's a fairly lengthy blog post, but it has a lot of pictures and things like that, so it's not too bad to read. We really want to get through this, understand everything that's going on, and especially these forward, backward, and Viterbi algorithms. And then we're going to take this and we're going to talk about, like I mentioned, we're going to talk about these notebooks, and then we'll have a really good understanding of how the forward backwards algorithm works and most likely state algorithm works. As I mentioned, the key here is, I add this, all of this live, is a good understanding of state space representation. Is one takeaway we should have from this, but then also getting a real good sense of smoothing and most likely state sequence algorithms and how they work in the discrete sense. That'll be our reading for this week. I might add a couple of more references in from other places that I've seen, but this is the bulk of it. I'm I'm gonna estimate this will be approximately 2 or 3 weeks. So, just so you folks know, I actually, if I'd already read these, then this wouldn't be a book club. So I have to then make a forward estimation of how much time it'll take. I'm gonna guess that we're gonna shoot closer for 3 weeks on this one to make sure everybody gets through everything. But all the details will be on Discourse, as you are familiar with. All right. I'm trying to think. That is it. We don't have a lot of questions today. Today, Girish asked, do state space metals handle non-ergodic processes naturally? I honestly have no idea. I'm going to have to research that question, so I would post that one into the Discourse. I don't have a good sense at this time, but we're going to find that together. Any other questions from folks? Any feedback on how today's session went? Again, the one thing I don't like about live streams is sometimes it's a very one-way communication. I can't see you folks. So are you folks confused? Was that the right level of material? Most importantly, do you folks feel like you are prepared to start diving into the material properly? Or are there any topics that you would like to see or get a refresher on before we start going into it in full? An important component of these book clubs that I want to point out is that we want everybody who joins to learn and make it to the end. Folks should end up with a good understanding of state space models. Maybe you're not able to derive state space models, but even just understanding the words and where they're applied is a win. And that's, let's say, the ideal outcome. But an outcome we're always going to avoid is people joining and getting confused and getting stuck and getting left behind. So anybody here feel like they're getting left behind, to ask that most directly? Or do you folks feel like you're properly prepared? To force an answer, I'm going to wait a really long time. An awkwardly long time. I have to both wait for the live stream to get to you, and then I have to wait for you guys to feel awkward to then give me an answer. So let's play this waiting game. All right. We've got one response, and maybe the others are coming in. Thanks, Ravine. It made me feel much more confident in the material and how to approach it. Okay. I'll take that one data point that I have right now as the Bayesian update that this had worked. I really appreciate you folks showing up and sitting through these book clubs. It's much more fun to do this together than it is to learn these things on our own. So, as always, I'm going to be... leverage the Discourse. I don't know if somebody asked a question here. Leverage the Discourse. Post your questions and whatnot here. I am going to open up a new topic, a new category for categorical HMMs down at the bottom here. So you'll see another thing here. I'll probably just label it HMM. So I'm going to open up a category for HMMs here that you can dump your HMM questions in. But of course, go in and utilize this however you like, whatever category makes sense for you. This particular thread is quite nice. Really get a good sense of where folks are coming from. It's also just a nice overview of our community. So go ahead and post in here if you like. And then, as always, if you want to post a more general introduction, you're always welcome to from here. Actually, there's some new ones. I should have been reading these. We have folks from South Africa, which I love. And then Sid from Boston. Sid is a regular contributor. I love chatting with Sid. Super fantastic guy. So, oh yeah, definitely do a Boston meetup. Oh, I'm not even showing you my window. Sorry, guys. I gotta stop doing that. To recap, I will add an HMM category down here. Go ahead in this topic and add your background and whatnot. I've linked that one in the chat. And then if you want to say hi, go ahead. And very much encourage in-person meetups. So a couple of folks last time had met in Portland, Julio, Bill, and Chad, and they had a great time. So anyone else that's in Boston, go ahead and meet up. I will host a Los Angeles meetup. If anybody is in Southern California or Orange County, I am happy to meet with any one of you. So do let me know. The last resource I'm going to show you is the repository. So let me see if I can pull it up real fast. So let's see if I can get it. I am going to be posting the code that I'm going to be using to learn in this book club here. The 3 notebooks that I went through are in this already, the environment and everything like that. So if you folks want to run any of the models and the Bayesian basic stuff, go right ahead. They're all there for your use. I will almost definitely be running code for HMMs on my own, so that'll be put in here as well. So this is another resource for you all. So with that, I'll take a final round of questions, and let me go through the last round of comments. Theo says, all good, comfortable with the stage. Thank you. Luke says, looking forward to it. Girish says, feeling quite comfortable. And Webster says, great session. So I think we're good. Jesus says, I am feeling comfortable with the material. The gaps will show as we progress. If there weren't any gaps, we wouldn't be learning, right? If we knew it all, we wouldn't need this book club. So I'm also looking forward to seeing what gaps I have in my knowledge, particularly with the newer ways to use state space models. With that, thank you folks for a wilder live stream, one that was a little bit longer and went over many topics. I appreciate you being here. All the details will be posted for the next book club on Discourse. With that, you know where to get started. Start reading about discrete hidden Markov models, and I will see you in a couple of weeks. All right.